Hello students, let us start our today's session from the chapter Aldehydes, Ketones and Carboxylic acid. Today we are going to discuss about carboxylic acids whose nomenclature, structure, preparation and properties we are going to discuss. So first of all, carboxylic acid, how do they get their name? The common name, actually the names arrived from their sources, but IUPAC name, actually it is alk plus ane plus oic acid. If at all saturated, we will use ane, or unsaturated, depends on the unsaturation, we may use ene or ine. So here we have taken only the saturated, so the name can be given alk plus ane plus oic acid, alkanoic acid. And this carboxylic acid, actually it has a carbonyl group and the hydroxyl group, and a compound can have one carboxylic acid group or two carboxylic acid group or even three carboxylic group. So depends on the number of COOH present in the compound can be classified into monocarboxylic acid, dicarboxylic acid or tricarboxylic acid. So when we have more than one di or tricarboxylic acid, we have to identify their position. And the monocarboxylic acid, always the carboxylic acid should be the terminal group of the given name, and the formula should contain the carboxylic acid at its terminal position. And any other substituents are there, those substituents will become as the prefix of carboxylic acid. This is why, because carboxylic acid group that has the highest priority while naming the functional group. So any other substituents are there, that becomes only the prefix of carboxylic acid. Let us discuss about some of the names. See, the first compound I have taken HCOOH. It is actually formic acid, because the sources, Latin name, Greek name and all we discussed in the introduction topic of this chapter itself. So formic acid, it has only one carbon, so its root word is meth and no double bond, so methanoic acid or it is methanoic acid. Similarly, acetic acid, CH3COOH, vinegar, and from which 2 carbon you are finding, so the name is eth, 2 carbon eth and oic acid, so the name is ethanoic acid. So CH3CH2COOH, where 4 carbon are there, so it is butyric acid, and in this case 4 carbon, its root word is butanoic acid, so the name is butanoic acid. And suppose if I write the isomer of butyric acid, you may find one of the CH3 that makes the branch, so it becomes isobutyric, because CH3 group is iso structure, as it has 4 carbons, so it is called isobutyric acid. Or when you say their IUPAC name, we have to start the numbering 1, 2, 3, and second position has methyl group, so the prefix is 2-methyl propanoic acid. And in this cyclohexane, we have a carboxylic acid. The common name as well as IUPAC names are similar. How we named C6, that is cyclohexane carbaldehyde. In place of COOH, if I have CHO, then the name is given cyclohexane carbaldehyde under aldehydes. Similarly, instead of aldehyde, I have COOH. So the name will be cyclohexane carboxylic acid. Both common name as well as IUPAC names are same. And this is benzoic acid. Actually, it has one carbon and the hydrogen is replaced by the phenyl group. From the formic acid, you can compare. Instead of one hydrogen, phenyl group is there, so we can say it is phenyl methanoic acid, but the benzoic acid itself taken as its IUPAC name, or we can write the name is phenyl, the suffix, prefix of the compound is phenyl, and it has one carbon atom, so we can write meth, then the prefix suffix is an, OIC acid. So instead of benzoic acid we can write even phenyl methanoic acid. So phenyl methanoic acid can also be given for benzoic acid, but the common name as well as IUPAC names taken as benzoic acid itself. Then in all these cases we have taken only one COOH group, so they comes under the part of monocarboxylic acids. And the rest of them I have taken two COOH group. The first member of the dicarboxylic acid is COOH. Its common name is oxalic acid. Actually this oxalic acid is present in tomato as calcium oxalate. So this oxalic acid, as it has two carbon atom, its name is ethane dioic acid because two carbon are there. So the name ethane dioic acid, we have to retain the letter E because it the first letter of secondary suffix starts with consonant. And similarly I can write butane dioic acid. 1, 2, 3, 4 carbon are there. So I can write it is butane dioic acid. We can give the position, but here we have all the 4 carbon atom considered. So we can write it, the name is butane dioic acid. Similarly, a benzene ring can have a dicarboxylic group. This is called phthalic acid, or it is benzene 1,2 dioic acid, as these carboxylic group are present at the first and second position of benzene. See, in this we will get different name. It has the isomer also. 1,2 benzene dioic acid is called phthalic acid. 1,4 dioic acid is called terephthalic acid, or 1,3 benzene dioic acid is said to be isophthalic acid. So we can have isomer of benzene dicarboxylic acid as phthalic acid, isophthalic acid and terephthalic acid with respect to the position of 1, 2, 1, 3 and 1, 4. Here I have taken only 1, 2. So the name is phthalic acid and its IUPAC name is benzene 1,2 dioic acid. Not only this, we can have so many number of dicarboxylic acid, and you know these carboxylic acids are commonly known as fatty acids. Why do they call it as fatty acids? The higher member of these carboxylic acids are found to be the glycerides, that is the esters of fatty acids. So vegetable oil or the ghee or any other the sources of will contain these carboxylic acid in their ester form. So most of the vegetable oils, they have contain these fatty acids in the form of esters. That's why the higher member of carboxylic acids are referred as fatty acids. Structure of carboxylic acid. Carboxylic acid, the central carbon, it has one doubly bonded oxygen with one OH group, and the next valency of carbon is bonded with an alkyl group. So this carbon, actually it is sp2 hybridized carbon, since it makes a double bond with the oxygen atom of carboxylic group. So sp2 carbon, that carbon it has 3 sp2 hybrid orbital of carbon atom, and that carbon it has one more electron in its px orbital. So this sp2 hybrid orbital of carbon that makes overlapping with one of the 2pz orbital of oxygen atom, and other 2 sp2 hybrid orbital of the central carbon that gets sigma bonded with sp3 hybrid orbital of alkyl group, and one more sp2 hybrid orbital that makes overlapping with oxygen atom of OH group. So in this oxygen atom of OH group, that is also sp3 hybridized oxygen atom. So the central carbon, it has 3 sp2 hybrid orbital. One of them makes sigma bond with 2pz1 orbital of oxygen atom, and 2 more sp2 hybrid orbital of central carbon that makes sigma bond with sp3 hybrid carbon of alkyl group and sp3 hybrid orbital of oxygen atom of OH. And because of this sp2 hybridized carbon, this central carbon, it achieves trigonal planar geometry and the bond angle is found to be 120 degree. And in this case, the pi bond is formed. Why the pi bond is formed? Oxygen, it has the 2s orbital electron and 2p4 electron. So this oxygen atom, it has two lone pair, those are from 2s orbital and 2p orbital. So one of the p set orbital that makes sigma bond with the sp2 hybrid orbital of central carbon atom. So it has one more orbital electron, this p orbital electron, and the carbon atom also has one p orbital electron. Those two p orbital that lies perpendicular to the plane of the trigonal planar and that undergoes the sideway overlapping that gives rise to the pi bond between the carbon and oxygen. This is what the structure of carboxylic group. And this carboxylic group actually acidic in nature. Why it is acidic? You know, the OH group, the COOH, as it contains one of the OH group, when the bond between OH is broken, it is able to give it as H plus ion. So the OH bond undergoes heterolytic cleavage where hydrogen gains the positive charge called as proton. So this group is said to be acid due to the donation of proton. So let us find the resonance in carboxylic acid. COOH I have given. This oxygen is more electronegative of the OH group and hence it withdraws the electron from the hydrogen atom. So we are getting minus H plus. Now this oxygen that carries the negative charge. Now this negative charge that can be delocalized between these two oxygen atom in such a way. So we may find CO minus and doubly bonded oxygen. So the negative charge of carboxylate ion can be delocalized between the two oxygen atom. So it gives rise to the resonating structure of carboxylic acid. Because of the resonating structure of carboxylate ion, we said to that the compounds are highly stable. Preparation of carboxylic acids. Carboxylic acids can be prepared by different methods. Let us see one by one. The first one is oxidation of alcohols. So from the alcohol chapter we are learning about oxidation of alcohol. It is a stepwise process. First of all, the alcohol undergoes oxidation to carbonyl compound and further oxidation that gives carboxylic acid. So in presence of a strong oxidizing agent, these primary as well as secondary alcohol can be oxidized to carboxylic acid, and the details of reactions we already discussed in both of the chapter, alcohol chapter as well as carbonyl compound. So this is the primary alcohol which is on oxidation. Always the primary alcoholic group undergoes oxidation to form carboxylic acid, that is the COOH will be formed. At the same time, when secondary alcohol undergoes oxidation, this CHOH R- group will be converted into COOH. From the secondary alcohol to carboxylic acid, number of carbon atom will always be lesser by 1 unit compared to the parent alcohol. So primary alcohol gives carboxylic acid where retains the same number of carbon, but secondary alcohol gives carboxylic acid but we will find 1 carbon less in carboxylic acid. And the next one from Grignard reagent. Grignard reagent, that could be an alkyl magnesium halide or even aryl magnesium halide. We can take any size of the alkyl group, but R group that can be changed, methyl, ethyl, isopropyl, butyl, any length of alkyl group we can take it with the Grignard reagent. So using Grignard reagent I am going to prepare benzoic acid. That's why I am taking C6H5MgX as my Grignard reagent. Actually to have carboxylic acid from Grignard reagent, it is just enough to take carbon dioxide. So this carbon dioxide, it is doubly bonded with the two of the oxygen atom, and one of the CO group undergoes nucleophilic addition reaction. So this pi bond attacks the magnesium MgBr group, and the C6H5 group attacks the carbonyl carbon. So we will get C6H5COO minus MgBr. It is said to be an adduct. This adduct followed by hydrolysis in presence of acid, we may find this OH group will attract that MgBr, and the minus of oxygen attract the hydrogen atom of water. So we are getting benzoic acid as the product. So as we have taken phenyl magnesium bromide, we got benzoic acid. If at all it is methyl magnesium bromide, the product will be ethanoic acid. But you know one thing, using Grignard reagent, we can't be able to prepare formic acid. So HCOOH cannot be prepared by using Grignard reagent. This is because this formic acid, it contains only one carbon atom, but the Grignard reagent is the step-up reaction. So it always increases the number of carbon atom in its product, and hence formic acid cannot be prepared by using Grignard reagent. The next one from nitriles. Nitriles are nothing but the cyanide. Here also you can take either R group or AR group. Alkyl cyanide or aryl cyanide undergoes hydrolysis. So the first stage of hydrolysis where the nitrile group is converted into amide group. So in this case addition of water takes place between the cyanide group where it forms C double bond O NH2, and this amide followed by further hydrolysis, and upon heating we will get carboxylic acid along with ammonia. So nitriles are converted into carboxylic acid, and this hydrolysis is said to be complete hydrolysis. So complete hydrolysis of cyanide gives carboxylic acid, or partial hydrolysis of cyanide will give amide. So this step is said to be partial hydrolysis. And one more, we can take this amide also to prepare the carboxylic acid. So this amide also can be a aryl group or even alkyl group. So this alkyl or aryl amides, upon hydrolysis in presence of an acid or a base followed by heating, we will get the carboxylic acid along with the formation of ammonia. Here we have taken benzamide. The name of the compound is benzamide. Upon hydrolysis it gives benzoic acid. The next method of preparation of carboxylic acid is from acid halides. The acid halides can be an alkyl acid halide or aromatic acid halide. So let us take either alkyl or aryl acid halides. They may undergo hydrolysis with water or even in presence of a base. But when these acid halides undergoes hydrolysis with water, where the reaction is found to be very slow. But at the same time, in presence of a base, the hydrolysis of acid halide that proceeds at a faster manner. So we are getting first of all the salt of carboxylic acid, followed by hydrolysis we will get the respective carboxylic acid. So let us take the two example, one from the aliphatic acid halide, the other one is aromatic acid halide. So CH3COCl, actually it is acetyl chloride, or you can say the IUPAC name ethanoyl chloride, because it has two carbon atom. So when this acetyl chloride it undergoes hydrolysis, you may find there is the removal of HCl, from which we are getting acetic acid and HCl. But the reaction is very slow because here no catalyst is present, either an acid or a base is not present. But at the same time, when the halide when the acid halide undergoes hydrolysis in presence of a base, where the base behaves as a catalyst and hence the rate of reaction, that is the hydrolysis of acid halides, will undergo fast. Actually it forms benzoic acid, but the presence of strong base that neutralizes the benzoic acid, that's why we are getting salt of benzoic acid. So it is nothing but potassium benzoate. So when this salt further hydrolyzes, it forms benzoic acid and potassium halides. Then from acid anhydrides, how anhydrides are formed? When two molecules of carboxylic acid is heated, there is a water molecule, removal of water molecule takes place between the carboxylic acid group. So this undergoes intermolecular dehydration of the two carboxylic acid, which results in the formation of anhydride. When this anhydride, see, upon heating only we are getting the anhydride. When water is used to hydrolyze the anhydride, once again we will get back the acid. That is what here we are using. This acid anhydride that can be hydrolyzed in presence of an acid. That acid, it behaves as a catalyst. So this water that can break either of the carbon oxygen bond or this carbon oxygen bond, where the water is shared among themselves. So we will get RCOOH, RCOOH. Two times of carboxylic acid formed. Let us take an example, acetic anhydride. This acetic anhydride is also known as ethanoic anhydride. When it is hydrolyzed by water, once again you can share the HOH between the acetate part and acetyl part. We will get two molecules of acetic acid. The next method of preparation of carboxylic acid is from ester. Esters are actually formed from alcohol and carboxylic acid. When ester is hydrolyzed by water in presence of an acid, once again we will get back carboxylic acid and alcohol. So this is called hydrolysis of ester, and this reaction is actually catalyzed by acid. So reaction always the carbonyl oxygen and the alkoxy group gets broken, so the H2O gets shared among these like this. So we will get RCOOH and R-OH we will get. Suppose if the ester is hydrolyzed in presence of a base, we will get the sodium salt of carboxylic acid, because soaps are the sodium or potassium salts of higher fatty acids. But here I have taken ethyl benzoate. So when it undergoes alkaline hydrolysis, once again the bond it breaks here, and this ethoxy group that removes that hydrogen atom of NaOH, I will get C2H5OH, and we have C6H5COONA. So this is called sodium benzoate. This sodium benzoate, upon acid hydrolysis, we will get back carboxylic acid and the sodium salt. This benzoic acid actually obtained upon the further hydrolysis of the sodium salt of carboxylic acid. The next one from alkyl benzene. It is very important one. Why? Because this is the alkyl group. It is present in the benzene as a side chain. This side chain that may go to any extent. So in such cases, the benzene, if it has the length of to any extent of alkyl chain, upon oxidation is simply oxidized into their carboxylic acid. So this formation of carboxylic acid is the irrespective of length of the alkyl chain. So this is what the beauty of the reaction, and it is undergoing the oxidation reaction only in presence of strong alkaline potassium permanganate. Here the alkali I have taken potassium hydroxide. So the formation of carboxylic acid due to the presence of the base, it gets neutralized to form potassium salt of benzoate. Upon hydrolysis I am getting benzoic acid. Okay, what could be the nature of the alkyl group? The alkyl group that could be a primary, secondary or even tertiary. Suppose if primary or secondary alkyl groups are present in benzene ring, that can easily be oxidized to carboxylic acid. Or if tertiary alkyl group is present and there the no oxidation reaction takes place, and we can say it has no effect towards oxidation reaction. So I have given the example. See, this is ethyl benzene. It is the primary one. And ethyl benzene on oxidation, it gives benzoic acid. And another one I have given isopropyl benzene, that is the 2-phenyl propane, it is the secondary. This is also on oxidation I am getting benzoic acid. But here I have the 2-phenyl 2-methyl propane, it is the tertiary carbon. This would not undergo oxidation though the oxidizing agent is strong. So the side chain alkyl benzenes, they may convert into carboxylic acid only if the alkyl chains are primary or secondary, and the alkyl chains irrespective of its length, it is simply converted into carboxylic acid. That's all the different methods of preparation of carboxylic acids. Physical properties of carboxylic acids. First of all, let us discuss about the physical state of carboxylic acid. These carboxylic acids up to having 9 carbon atom, they may exist in colorless, pungent smelling liquids. But when the number of carbon atom goes beyond 9, those becomes the wax-like solids of colorless, odorless one. So the lower member, that means compounds having up to 9 carbon can be in a liquid state, but others are in solid state. Then boiling point. Carboxylic acids, they possess the highest boiling point compared to alcohols, carbonyl, ether and even hydrocarbon. This is why, because carboxylic acid, it possesses intermolecular hydrogen bonding, because it has COOH group and another COOH group I have that makes the hydrogen bond between the carboxylic acid group. And this hydrogen bond is not only present in its liquid form but even in the vapor phase. These carboxylic acids are exist as dimer. When it goes dimer, the molar mass of the carboxylic acid gets increased and hence its boiling point will be changed. So these carboxylic acid, they could exist even in their dimeric form in presence of aprotic solvents also. So not only in the vapor phase but even in presence of aprotic solvent, this carboxylic acid exists as dimer. And this hydrogen bond is not even completely broken in the vapor state also. Because of the existence of hydrogen bond both in vapor phase as well as in its liquid state, they possess the highest boiling point compared to alcohol, carbonyl, ether or hydrocarbons of their comparable molar masses. The next one, solubility. We know well only the lower members of carboxylic acids are able to miscible with water. But when the higher member it goes, the alkyl group size bulkier and hence the miscibility with water decreases because of the hydrophobic nature of the alkyl group. And benzoic acid, though it is the first member of aromatic carboxylic acid, is merely insoluble in water. So the next one, glacial acetic acid. Glacial acetic acid is nothing but the pure form of acetic acid. Actually, vinegar is 5 to 8% of acetic acid is known as vinegar. But in this case, when acetic acid is cooled down to 289.5 Kelvin, where the liquid form of acetic acid is converted into solid form of acetic acid. And in this case, the solids of acetic acid is exist like ice-like crystals. That's why it is said to be glacial acetic acid. That's all the physical properties of carboxylic acid. Chemical properties of carboxylic acids. This carboxylic acid that may undergo the 4 different types of chemical reactions depends on the cleavage of the bond or the nature of group taking part in chemical reaction. Suppose if there is the cleavage of oxygen-hydrogen bond, then carboxylic acid gives rise to the reactions due to the cleavage of OH bond. Or if the cleavage of CO and OH bond takes place, then the reactions due to cleavage of COH bond, where the OH group becomes the leaving group, and in the previous case the hydrogen will become a leaving group. Or the compound that may undergo the both reactions of the involvement of carboxylic group itself, there it forms the hydrocarbon, that means the decarboxylation reaction that may undergo. Similarly, the alkyl part of the carboxylic acid may also undergo chemical reaction. So we have reactions involving alkyl part. Let us see first of all reaction due to cleavage of OH bond. In this case, the hydrogen atom becomes the leaving group of the carboxylic group. So let us have the reactions with the metals and alkalis. The alkalis that could be a strong alkali or even weak. So we can have strong bases as well as weak bases. So carboxylic acid being stronger acid, so we can have that metal can displace the hydrogen from the carboxylic acid. So this hydrogen atom is displaced by the sodium metal. So we are getting sodium carboxylate. Or if you have a strong base like sodium hydroxide NaOH, there is the formation of water between the NaOH and carboxylic group. Once again we will get sodium carboxylate. As well as this can also react with the weak bases like sodium hydrogen carbonate. This involves the formation of water molecule, carbon dioxide as well as sodium carboxylate. But this one we can take it as test for carboxylic acid. Why it is called a test for carboxylic acid? Because carboxylic acid on reaction with the carbonates or bicarbonate that evolves the carbon dioxide. So the release of carbon dioxide that makes brisk effervescence to the reaction. So from the brisk effervescence we may identify the given organic compound contains carboxylic acid group, and moreover these carboxylic acid they usually turns blue litmus to red. That's all the reactions where the cleavage of oxygen-hydrogen bond takes place and we get the salt of carboxylate groups. The other set of reactions in which the cleavage of COH bond takes place. So the OH group becomes the replaceable group. So it can react with the phosphorus trihalide, pentahalide or thionyl chloride. Let us have different examples for these three different halogenating agents. So ethanoic acid with the phosphorus trichloride, this OH group is replaced by this chlorine atom. So I have 3 chlorine, so should take 3 times of ethanoic acid. So we are getting 3 times of ethanyl chloride, and this HO with the phosphorus that makes phosphorus acid. With benzoic acid, phosphorus pentachloride that may form HCl and POCl3 along with C6H5COCl. So we are getting benzoyl chloride and phosphorus oxychloride HCl. Similarly, if we have propanoic acid CH3CH2COOH is taken, here also the COOH group that can be replaced by one of the halogen. So I will get CH3CH2COCl, that is propanyl chloride, sulfur dioxide and HCl. The next reaction is esterification reaction. Esterification is nothing but the formation of ester from acid and alcohol, that only esterification. The reactants are, one of them will be the carboxylic acid other will be the alcohol. So when they do react in presence of concentrated sulfuric acid, we will get ester and water. And the reaction always in equilibrium, because the reverse reaction is possible, because the ester that can be hydrolyzed by water to give back acid and alcohol. So to prevent the reverse reaction or to shift the equilibrium in the forward direction, sulfuric acid is taken, so which is used as the dehydrating agent. That's why the reaction always pushes towards the forward direction. In place of carboxylic acid, aliphatic carboxylic acid, we can even take aromatic carboxylic acid. So benzoic acid with methanol, there also formation of water. So we are getting C6H5COO CH3. So it is methyl benzoate. This is what? Esterification reaction. So in esterification reaction, carboxylic acid with alcohol, in presence of acid we will get ester and water. That's all the reactions in which the cleavage of carbon-oxygen bond taken place. The next one, reactions involving carboxylic group. Here the carboxylic group is completely converted into some other groups. So when carboxylic group are reduced by lithium aluminum hydride, it forms primary alcohol. So we have to remember, upon the reduction of carboxylic acid, it always gives a primary alcohol, and the reduction usually carried out in presence of lithium aluminum hydride only. So COOH is converted into CH2OH. It involves 4 times of hydrogen, so there is a loss of water molecule also. The next one, reduction of carboxyl into alkane. This hydrogen iodide that reduces that COOH group completely into another methyl part. So we are getting the ethanoic acid into ethane. So carboxylic acid can even be converted into hydrocarbon by reduction with the red phosphorus at 473 Kelvin with hydrogen iodide. And decarboxylation. Decarboxylation, it involves removal of CO2 group. So that can be done by the decarboxylating agent. What is called decarboxylating agent? This sodium hydroxide and calcium oxide mixture in the ratio of 3:1 is called decarboxylating agent. For this decarboxylating reaction, we have to take sodium salt of carboxylic acid. So first of all, carboxylic acid is treated with the base. There we are getting the sodium salt of carboxylic acid upon heating with the soda lime, where we may get Na2CO3 as a product. So CH3 with the H, we are getting hydrocarbon. And the same carboxylic acid that can be undergone that Kolb's electrolysis. In Kolb's electrolysis, we will get the higher member of alkane, but in decarboxylation of this carboxylic acid, it has 2 carbon atom, but the product it has 1 carbon atom. So the decarboxylation reaction always results in the lower member of hydrocarbon, but Kolb's electrolysis of carboxylic acid that gives the higher member of alkane, because in the carboxylic acid, the decarboxylation reaction, we have 2 carbon atom in this carboxylic acid, but it is now reduced to only 1 carbon in the alkane. So in Kolb's electrolysis, we have to take the aqueous solution of sodium salt of carboxylic acid. When it undergoes electrolysis, actually it is split up into carboxylate ion and sodium ion. This sodium ion is converted into sodium hydroxide and hydrogen. This is why, because the presence of water that to take part in the reaction, and hence we will get sodium hydroxide and hydrogen. Hydrogen will be liberating at the cathode. But in this case, the acetate ion is liberating at anode, where we are getting the higher member of ethane and carbon dioxide. The next one with the ammonia. Actually, carboxylic acid immediately reacts with ammonia. This is why, because ammonia is a base. So this is an acid, this is a base. So an acid and base reacts to form the ammonium salt of carboxylic acid. Here the carboxylic acid can be of aliphatic or even aromatic. So I have taken R or AR. You can place R in place, you can write CH3, AR in place, you can write C6H5. So the reaction will proceed like RAR, the ammonium salt of carboxylic acid. This is on heating, there is a loss of water molecule, so ammonium salt is converted into amides. The last reaction, action of heat. When two carboxylic acids are taken and heated in presence of phosphorus pentaoxide, it is a dehydrating agent. There is a loss of water molecule between the carboxylic acid group. So this is called intermolecular dehydration of carboxylic acid that results in the formation of anhydride. So that's all the reactions in which the entire carboxylic group is converted into either alcohol or hydrocarbon or amide or anhydride. Reactions involving alkyl group. So where the carboxylic acid containing alpha carbon, the hydrogen that is present in alpha carbon can be displaced by the halogen atom in presence of red phosphorus and halogen. This reaction is known as HVZ reaction, that is hell-volhard-zelinsky reaction. So let us take ethanoic acid, that is acetic acid is taken, in which this is the alpha carbon because this is the functional group. Functional group attached carbon is alpha carbon. This alpha carbon, it has 3 replaceable alpha hydrogen atom. So that can be replaced by the halogen atom in presence of red phosphorus. We will get monochloro, dichloro, trichloro derivatives of acetic acid. So successively one of the hydrogen is replaced by halogen. So we are getting CH2ClCOOH. It is alpha chloroacetic acid. When another hydrogen is also replaced by the halogen, we are getting dichloroacetic acid. Where the next hydrogen is also replaced by chlorine, we will get a trichloroacetic acid. Then reducing action of acetic acid. This is very important reaction because all other carboxylic acid do not reduce Tollens reagent or even Fehling solution. But only the formic acid can reduces the mild oxidizing agents Tollens reagent and Fehling solution. This is why, because when we write the structure of carboxylic acid HCOOH, see this formic acid, it has the aldehydic structure as well as carboxylic acid structure. So due to the presence of aldehydic structure in formic acid, it is capable of reducing both Tollens reagent as well as Fehling solution. So when we have Tollens reagent, that is that ammoniacal silver nitrate solution, here the biformate ion is converted into carbonate ion. The formate is converted into carbonate, where silver plus ion is reduced to silver mirror and water is produced. Once again we have to balance the charges. I have negative charges twice the time in product side. So correspondingly I have to balance, this is by 3 times, this is by 2 times. So 3 minus 2 plus negative minus 1, this is also minus 1. So here the charges balanced. Similarly, formate ion can reduce Fehling solution to the red formation, the red precipitate of copper 1 oxide. Here also we have to balance copper 2 times, so 2 Cu2 plus taken, but carbonate ion, it has a di-negative charge and hence the OH multiplied by 5 times. So 5 minus with 1, 6 minus, 2 2s are 4, 6 minus 4 plus, that becomes 2 minus. So we are getting carbonate ion and the red precipitate of copper 1 oxide along with water. Water 5 hydrogen plus 1 hydrogen 6. So there would be 3 molecules of water. That's all the chemical properties of carboxylic acids. Electrophilic substitution reactions of benzoic acid. Just like aldehydes and ketones, carboxylic acid also deactivates the benzene ring towards the electrophilic substitution reaction, because we know the carbon-carbon which are directly attached in the benzene ring and the carboxyl group, no difference in electronegativity. But the carbonyl oxygen, they differ in their electronegativity, and hence this oxygen withdraws the electron from the carbonyl group. So we are getting CO minus, where the electron density of carbon decreases, and hence the one of the pi bond that migrates towards the carbonyl oxygen. So it develops a positive charge at the second position, and it proceeds with the further resonating structures. We are getting the positive charge at the fourth position, and this pi bond moves towards this positive charge. So we are getting the positive charge at the sixth position. So because of the formation of positive charges at 2, 4, 6 position, this could able to direct the incoming electrophile to the meta positions alone, because these meta positions do not have any charges. It is a neutral position, and hence the electrophile which do not find any repulsive forces, so it may attack that third position of the benzene ring. And moreover, these aromatic aldehydes, aromatic ketones and aromatic carboxylic acids do not undergo Friedel-Crafts alkylation, acylation or even benzylation reaction. This is why, because all these aldehydes, ketones and carboxylic acids are deactivating the benzene ring, and hence the Friedel-Crafts reaction does not take place in aromatic benzaldehyde, acetophenone, benzophenone and benzoic acid. Now let us see some of the electrophilic substitution reactions of benzoic acid. And we said carboxylic acid is a meta-directing group. So the meta position of hydrogen can only be replaced by the electrophile. So during the bromination, in presence of ferric bromide, we need the catalyst because of the deactivating nature of carboxylic acid. It gives meta-bromobenzoic acid. Or if it is nitrated in presence of concentrated nitric acid and concentrated sulfuric acid, this hydrogen may combine with the OH of nitric acid to form meta-nitrobenzoic acid, or with the fuming sulfuric acid. Fuming sulfuric acid is nothing but oleum. It gives rise to the meta-sulfobenzoic acid, because the COOH takes the priority, following that the sulfonic group, and hence the name is meta-sulfobenzoic acid. That's all the electrophilic substitution reactions of benzoic acid. Okay students, let us close our today's session. Today we have discussed about nomenclature, structure, preparation and properties of carboxylic acids. We have some more topics to discuss about this chapter. So let us continue our next session. Until then, bye bye.